Hi there. Today we're going to keep going in Chapter 11, and we're going to look at special kinds of power series called Taylor and Maclaurin series. So let's get going. So what we're going to do here is we're going to build a custom power series using derivatives. And the idea is we're just assuming that f is a function with a power series, so it has to look like this. And we're just going to see if we can learn something about these coefficients just from the function itself. And we want to get all the CNs in terms of f, somehow, f or its derivatives. So when we start here, this is equation 1. If we plug in x equals a, everything drops out because everything's 0 except this first term. So that means f of a is actually c0. Now this should make sense because we're trying to approximate a general function with a infinitely long polynomial or whatever it happens to be. A power series, right? Kind of looks like this. And so we would expect that at least one point that the two different representations have to touch. So that's what we're saying. We're basically saying, so at a, where the x coordinate is a and the y coordinate is c0. So at the point a comma c0, the actual function f of x and its power series representation touch at least that point. Maybe they touch at other points too, but we're just building this thing from scratch. Now we take the derivative of both sides, and over here we get the power rule. So all these powers come down, right? So this was a square, it comes down. This was an x minus a to the 0 power, so that's anything to the 0 power is 1. Same thing here, right? This was a 3, it comes down. This was a 4, it comes down. And then we can see that plugging in a again, we get f prime of a is c1. So think about what that means, right? That means the first derivative of the original function and its power series representation has to be the same at this point. So if we can just keep matching derivatives, right? So the function itself at that point matches. The first derivative at that point matches. The second derivative, right? So like the concavity matches, et cetera, et cetera. So if you keep matching up all the derivatives of this function at this point, you get to see what happens. So here's our second derivative. Again, this was an x minus a to the 0, so it goes away. The 2 came out front, the 3 came out front, and now we get f double prime of a is 2c2, right? Because it's the only thing left over after we plug in x minus a. And if we do it one more time, you can keep seeing the pattern. So here's the third derivative. This was an x minus a to the 0. This 2 came to the front. Plug it in, and we get f triple prime of a is, because this, everything to the right of that becomes 0 when we plug in x equals a. And there's a pattern there, right? What we've seen is that if we keep differentiating and plugging in x equals a, every term to the right drops off. So you're left with a single term, and that single term has all of the previous exponents multiplied out as it started to move to the left. As things to the left became 0, things to the right become 0, there's always exactly one thing left over. And it turns out it's just this. It's just n factorial times cn. But we're trying to solve this for cn. We want to know what cn is. So it's just the nth derivative at a over n factorial. And we just proved the theorem that we're going to use to do work for the rest of this section. This was actually, we started with the proof. It's this. It's saying that if f has a power series representation at a, given by this, remember this is what we had from a previous section when we did power series, then the coefficients are given by this. And when we just take this and plug it back into this formula, we get this. This is called the Taylor series representation, and this is what we're going to be using to do all of the work for the rest of the section. So the only thing different about it compared to this is when we saw power series earlier in earlier sections, we didn't know what the CNs were. Now we do. And this is how it looks expanded out. So sometimes we call it the Taylor series. Sometimes we call it the Taylor series expansion. Centered at A, about A. There's lots of different ways people say this. But it always looks like this. And you might as well just memorize it, like I said, because that's what we're going to use to do all the work. So we're going to take a bunch of derivatives, plug in A, and look for a pattern, and then we simplify that pattern. There's always a factorial in the denominator, and you always have an x minus A to a power. Then there's another type of series called a Maclaurin series, which is just a special case of the Taylor series where A equals 0. These are generally much simpler to compute, and so we're going to jump back and forth between Taylor series and Maclaurin series. For now, if you just want to call a Taylor series at 0, if you want to call it that, that's fine. But in the text or in the homework, if it says Maclaurin series, then you have to know that that means Taylor series with A equal to 0. It's just an easier type of series to compute. So we do some work with these first, and then we generalize it to the larger Taylor series. Now, we're going to be finding Taylor series, but just keep in mind that there's no guarantee that the sum of a Taylor series is in fact equal to f. There are functions that pop up that don't have Taylor series representations. What the theorem says, so what this theorem says here, is that if there is a power series representation, then that power series representation is the Taylor series. It's not saying every function has a Taylor series. Those are not the same statements. It's saying if it has one, then you can find it with a Taylor series, or it's equal to the Taylor series. And again, there are functions that are not equal to their Taylor series sums, like this one here. So we're not going to do any more work with those that don't have Taylor series. The vast majority of functions do, that you will ever see. And as we saw in previous sections, there are series that are only able to be represented by power series. Functions that are only able to be represented by power series. So this is a very useful and powerful tool in science and engineering. All right, so let's do an easy one. This is the easiest one that you're going to see. We're going to do two easy ones. So we're going to do a Maclaurin series and find the radius of convergence for f of x equals e to the x. So the first step is always compute all the derivatives. And plug in a. In this case, a is 0. But e to the x has the easiest derivatives, right? It's just itself. So that really simplifies the calculations when we go to plug stuff in, right? So all the derivatives are e to the x. When we plug in 0 into all these derivatives, we get 1. So the Maclaurin series then, for e to the x, here's the formula. But wherever it's just fn of 0, right? This is every derivative. I just replace this with 1. So it just goes away, and I move to the x to the end of the numerator. And then I write it out like this. So you can see what a powerful tool this is. So I can, if I want to find e to the first power, it's just 1 plus 1 over 1 factorial plus 1 over 2 factorial, right? So e to the first power, numerically, is just 1 plus a half plus a sixth, and so on and so forth, if you compute these out. So if you're using computers to evaluate something in a function, much easier just to use the Taylor series, or in this case, the Maclaurin series. Now, we want to find the radius of convergence. That's going to be the ratio test. This one's real easy to do, the ratio test. Right, you can see what happens here. The n plus 1 factorial cancels with the n factorial and just leaves an n plus 1. The x to the n plus 1 and the x to the n cancel back down to an x. The absolute value, you don't need it around the n's. Those are all positive. But the idea here is that no matter what happens, right, this limit is 0. So as we take n very large, for any value of x, n eventually gets larger. So the radius of convergence is all x, and the radius is infinity. We saw this exact ratio test in an earlier section. So just remember that when we're checking, when we use the ratio test and then you need to check endpoints, you only need to check the endpoints when the radius of convergence is finite, right? So obviously with an infinite radius, there's no endpoints to check, so you don't need to do that. Okay, so now we're going to talk a little bit more broadly about Taylor series. Again, there's plenty of calculations coming up. So under what circumstances is a function equal to the sum of its Taylor series? In other words, if f has derivatives of all orders, when is it true that f of x equals the Taylor series sum? So we're going to do a theoretical aside. You don't have to do any calculations for this, but you should know just sort of theoretically why this works. And in order to see how it works, we need to talk about Taylor polynomials. F is the limit of the sequence of partial sums. And so we're going to label that sequence T for Taylor. And it's the subscript n means that it depends on n, right? It's a function of x, but the length of the Taylor polynomial is based on n. So we just put a little subscript there. Because if you write t of x, we're saying that that's a function that doesn't necessarily depend on n, but it's t sub n of x. And it's just the sum from 0 to n, and then of the i's here. So it looks like this. So the only difference between a Taylor polynomial and a Taylor series is that the polynomials are finite. So the idea is, if we're using polynomials to approximate some sort of function, we just want to know, is the limit of these approximations approaching 0 as n gets bigger? Well, we can see with e to the x, because that's the one we just did. Here's the first 3 Taylor polynomials. Right? You can do t0, but it's just a horizontal line 1. And you can see that these approximations are getting a little bit better, right? Here's 1 plus x. Here's 1 plus x squared over 2, and so on and so forth. So as you put more and more Taylor polynomials, the approximation gets better and better. And if you were allowed to take this thing infinitely long, the polynomial would in fact match up with e to the x. But as of right now, these things only touch in a single point, right? At 0, 1. But they have the same derivative, same second derivative, etc., etc. So when we're trying to prove that a function does in fact have a Taylor series representation, all we want to do is just show that that the difference between the Taylor polynomial and the original function goes to 0. We're not going to do the proof. That's just theoretically kind of going on under the surface. It would be no problem to prove it, but this section is it's already super duper long. I'm not trying to make it longer. So the idea here is if you just take the function and subtract Tn of x and call this the remainder, then what we're really saying is that the limit of the remainder as n goes to infinity would be 0. That's what we're really trying to do here, right? So if we can somehow show this remainder goes to 0, then we will have proven this thing, right? Because Tn is just the difference between the function and the remainder. If we can show this goes to 0, then that limit will be 0, which will be f of x. So that's the idea. It's actually, for most of these functions, really easy to show that the limit of the remainder goes to 0. A lot of times it does, in fact, involve some calculation. Again, we're not going to be doing it. We'll be doing other things to show how these approximations work. But this is, in fact, the way that you would do it. All right, let's talk about 2 theorems. So the first one is, if the function is the Taylor polynomial plus the remainder polynomial, well, this is just remainder, is just a function of x. And if the limit of the remainders goes to 0, then f is equal to the sum of its Taylor series. So again, I'm not proving this either. What I on the previous slide is basically a sketch of a proof. But this is more just something that should make sense, right? As you add more terms, if the remainder gets smaller and smaller and eventually becomes 0, so the limit, it can be as small as you want, then we're basically just saying that f is equal to the sum of the Taylor series. There's one other thing, and again, we're not doing any work with this, but it is important to at least be able to read it. So this is saying if the next derivative of the function is less than some value m on some interval, so d is just a number, right? Then the remainder satisfies this inequality. So this is called Taylor's inequality, and it's what we use to show this if we were to do it. You're basically just doing like a ratio test with this. So that's how it would be done. Again, I'm skipping it just for this particular class because it just takes too much time. But if you're interested in this stuff, it is in the book, and you can watch YouTube videos and stuff about it. So again, this is just a sketch of how we would show this but we're not getting into the details. It's just too long. All right, so let's keep going. So this is just, from this point forward, we're basically just going to be crunching a lot of numbers, looking at a lot of functions, and finding a lot of Maclaurin and Taylor series. All right, so we're doing sine x. In the previous example, we used e to the x, which has the easiest derivatives possible. But sine x has some pretty easy derivatives, but it's not the easiest derivative. So, you know, the function evaluated at 0 is 0. Take the derivative evaluated at 0, you get 1. Take another derivative. Negative sine of 0 is 0. Keep taking derivatives. Now we get negative cosine, which is negative 1. And when we take that fourth derivative, we're right back where we wanted to be. We're right back at 0. So the pattern repeats from here. So when we're trying to come up with what's the relationship between this number in the right-hand column and the number that's attached to the derivative, right? It's not clear what the relationship is. But here's what's nice about this. If we get 0, then whatever term uses that 0 is going to completely go away. Remember, we're multiplying by the derivative at 0. If you look at the formula, right, it's multiplication. So what happens is anything that becomes 0 just goes away. So here's our formula, right? So fn of a, right, that's this. A in this case is 0. So every other term is going to go away. So I just wrote out the function, all expanded it. We know a is 0, so everywhere I see a, I plug in 0. And you can see that we've already computed these values. Every other term just goes away, right? These are all zeros. So I just simplified it. Now, let's get rid of all the zeros and see what we have left over, right? We just have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Well, that simplifies really, really nice. And then we use what we developed earlier with sequences and early on in chapter 11 to write that in a nice closed form. You notice it's an alternating series. The first term is positive. So if we start with 0, we want this to be an n. And then just look at the exponents, right? This is x to the 1st over 1 factorial. That's a pattern. It's right here. So it's odd numbers. Odd numbers are 2n plus 1. And so it's x to the odd number divided by the same odd number factorial. And we're done. And then you would use the ratio test to do the radius of convergence. So I'm not doing all the ratio test work in the notes here. Again, trying to cut the time down a little bit. This one is a very easy ratio test. Go ahead and do it on your own. And so what happens is, so we know e to the x. Now we know sine of x. This is the method you use. Compute a bunch of derivatives, plug it into the formula, look for a numerical pattern, and then look for a numerical pattern and then condense whatever the pattern is here. Just condense it into a smaller form. All right, let's keep going. So now we're doing a Taylor series, not a Maclaurin series. And we're going to do natural log of x with a equals 6. And I will be doing the ratio test on this one for the radius of convergence because I want you to see it. So you start taking derivatives, right? Now this one is sufficiently complicated that I had to kind of table it just to look at what was going on. So the zero derivative is just the function, but it's still natural log of 6. First derivative is 1 over x, which is x to the minus 1. And then plug in 6, right? 6 to the minus 1 power is 1/6. Second derivative, we get the power rule. Drop the power by 1. Plug in 6. Right? And you get negative 1 over 36 and keep going. You, on the left side, if you're making these tables, you want to keep these numbers separate so you can see what's happening. On the right side, you want to simplify it. Sometimes stuff cancels. Sometimes it doesn't. I would caution you against putting these numbers in lowest terms. The whole point of this thing is to find some sort of pattern. On the right side, starting here, it's basically a factorial in the numerator, right? 0 factorial is 1, just for the record. So if we make this the 0 term, 0 factorial, 1 factorial, 2 factorial, 3 factorial. And then here, this is just 6 to the n. You want to avoid simplifying this because you're not going to see the numerical patterns. They just go away. So if you're looking at like answer keys or you're looking stuff up online if you want more practice, a lot of times they simplify this and it doesn't help. Don't simplify this. Keep it expanded so you can see what's happening. And then over here, it's very expanded. Because over here, I need to find the overall numerical pattern, right? So notice, not counting the first term, but starting here, it goes even, odd, right? In terms of like the power, what we're going to have here. So it's positive, negative, positive, negative. So this is a negative 1 to the n plus 1. Because we want to start with this first term. We don't want to start with this 0 term. Because it's not going to work. So we're gonna kind of make this term sort of separate. We're going to start with this. Because it starts to alternate. This one doesn't alternate. Because it goes like positive, positive, negative, positive, negative. You want to find where it starts to alternate and put that, a minus 1 to the power. And then also in the numerator here, so these are these numerators, right? These x's are denominators, these numbers are numerators. You can see that it's just n minus 1 factorial, right? So when n is 4, it's 3 times 2 times 1. When n is 3, 2 times 1. So it's n minus 1 factorial. And of course in the denominator, this is the first derivative, so it's a 1. Second derivative, there's a 2. So it's just x to the n in the denominator. So you can write it x to the minus n and put it in the numerator. You're allowed to do that. That's generally not how we do it because you end up wanting to use the ratio test to find convergence and divergence. The ratio test works better with fractions. So over here, this is the same thing. So this is the general form of the function, but I need to plug in 6. So this is what I'm going to use. I have to plug in x equals 6. So this whole thing, exactly the way it appears, gets put into the equation. Right? Plug in a equals 6 and f n of 6 into the formula and simplify. We still need to check and change the initial value of n because f of 6 doesn't have the same form as the derivatives, right? We saw that earlier. These are all fractions. This isn't. And so we're going to set that 0 term aside. So here's the general form, but we're going to set the 0 term aside. Here it is. It's out of the way. We're going to start with n equals 1. This whole thing came from here. So where I see this, I just plop this guy right in there. And then you simplify if you can. Here we have an n minus 1 factorial over n factorial. That will reduce to just an n in the denominator. And then I kind of squished everything else together. And you're done. That's the answer. So one thing about these problems is don't oversimplify. It's just gonna look like this. Right? It might be alternating, it might not. It might have some n's and some 6 to the n's in the denominator, it might not. It might have an x minus 6 to the n. We'll just have to see. And again, I pulled out this term because it didn't fit into the form of the derivatives, right? All right, let's keep going. Oh, we got to find the radius of convergence. That's right. So do the ratio test. There's that big honkin' ratio test. It simplifies pretty nice. All the negatives go away, so you just ignore them. And then I just flip and multiply. And you can see what's going to cancel. The n and the n plus 1 I'm going to pull out front of the absolute value. The 6 to the n, 6 to the n plus 1, that just reduces to a sixth. I'm going to pull that outside the absolute value. What remains inside the absolute value is going to be x minus 6. Here we have an n plus 1 and an n. That's going to cancel down to x minus 6. I also fixed up this n over n plus 1. I divided by the highest power in the denominator. Took the limit. Right, the limit of this is 1. This stays a sixth. And again, with the ratio test, you want to make sure it's less than 1. But this is the same thing as just multiplying both sides by 6. So the radius of convergence is 6. And if this were a longer problem, I know it's already a pretty long problem, you would check the endpoints for convergence or divergence. Generally speaking, if you're using the ratio test, they do tend to diverge at the endpoints, but you still should check. All right, next up is something called a binomial series. This is a special kind of power series. And it has this formula. So if you have 1 plus x to any real number power, right? It doesn't have to be a whole number. Then this is the power series. It's just k choose n, x to the n. So this is a pretty interesting thing because of the way it expands. And you just use the formula for k choose n. So as you go to the right, you pick up multiplying k minus more and more stuff over n factorial. Because of this formula, everything else will cancel. I'm not doing the proof of this formula here, but if you want to work it out on your own, you can. It is the right formula. All right, so let's see how to use this. So let's expand this function as a power series. Well, the fifth root of 1 minus x is, you got to put it in the right form. It has to be 1 plus something to the power. And in the formula here, in the example we're doing, this is negative x. You plug negative x in here, and k is 1/5, right? So k is a number, so you just write 1/5 choose n minus x to the n. This has to be in parentheses, you will get it wrong. Then we just plug everything into the other formula, right? It's 1 plus kx, but here x is minus x. And then it's k times k minus 1 over 2 factorial, and then the minus x squared. So you're just plugging everything from this formula into the other formula a couple slides ago. So keep those formulas out. I'm not computing this. I just know what it's supposed to look like from the patterns. Simplify. Notice that every other term is negative, at least at this stage, right? So it looks like the series is going to alternate, but it doesn't, because we're also picking up negatives in the numerator. Every new term, we're picking up an extra multiplication of negatives. So what we have is an alternating series sitting inside an alternating series. And it turns out all the terms become negative. Who knew? So you can see what I'm doing here. I'm pulling these 5s down into the denominator. Then I'm just multiplying the numerators. And the negatives, just for every other term, wherever it's positive, there's an odd number. Wherever it's negative, there's an even number. So they all just become negative. And you can see what's going on in the numerator here. It's 1, 4, 4 times 9. And if we continue this pattern, you actually pick up, I didn't show it in the slide, but if you were to do one more, This numerical pattern, 4, 9, 14, is going up by 5s every time. And you can see why, right? We have a fifth minus 1, a fifth minus 2, a fifth minus 3. So we're always subtracting 5/5 as a new multiplicative term. So those numerators are going to be going up by times 5. Well, adding 5 and then multiplying, right? So this 1 is really irrelevant. Some of you might notice that, well, if it's 14, 9, 4, 9, 4, 4, couldn't you just tack on -1? Wouldn't that explain for all these minuses? You could do it that way. I'm choosing not to do it that way. It's just way less confusing where I come from. Because these problems are confusing enough, trying to find these numerical patterns. So we definitely have a 5 to the n in the denominator. We definitely have an n factorial. We definitely have an x to the n. What's the relationship between these numbers and n? You have to take out that k minus 1 and put back in something that is a function of n. And again, notice the numerical pattern in the numerator doesn't start until the n equals 2 term, right? The going up by 5 each time doesn't start. So I'm pulling the first 2 terms out. And then this minus sign is just distributed. So this is a sum, but all the terms inside are going to be negative. We're starting at n equals 2. N equals 2 corresponds to 4. N equals 3 corresponds to 9. And so all you have to do is just build a linear, it's just a linear function. It's just point slope form, basically. So what's the relationship? 2 gets mapped to 4, 3 gets mapped to 9. You do rise over run. You know how to solve these. And you get 5n minus 6. And it checks, right? If you plug in 2, 5 times 2 is 10, minus 6 is 4. So that first one is a 4. Plug in 3. 5 times 3 is 15, minus 6 is 9. So you get 4 times 9. Keep going. You eventually get 14, then 19, and so on. Everything else, we already know what it looks like. And we're done. That's the end of the problem. So this doesn't look like much of a problem because this is a very confusing notation. What you have to remember is, though, this is telling us term by term what the build-out looks like, right? This is not a function here. This is what one term in this large function looks like. So it takes some getting used to in terms of how it looks, for sure. Let's keep going. All right, we got basically one more topic. One more new topic. And then one more big example. So it turns out that we can make new Taylor series out of old ones. So no matter how a power series representation for a function is obtained, it must be the Taylor series of f, right? And that's what we proved very first slide, right? Or first set of slides. Is that if f has a power series representation, then it is the Taylor series. So we can obtain new Taylor series representations by manipulating series given in a table. So if we know something about a series, we can just add, subtract, multiply, divide, integrate, differentiate, stuff like that. This coefficient formula from our earlier theorem is much harder to use. And as we saw in examples last section, we can replace x in a given Taylor series by an expression of the form cx to the m. We can multiply or divide the series by such an expression, and we can differentiate or integrate term by term. So what we're saying here is that you can't like put a Taylor series inside another Taylor series. So if you know the Taylor series for like e to the x, let's say, you can't do like e to the sine x and start inserting Taylor series. But if your substitutions are only polynomials and constants, multiply, divide, add, subtract, differentiate, integrate, then yes, you can. So let's see how to do it. Oh, first I did want to talk about this. This is just a few of the very common Maclaurin series. This one is a geometric series. We proved this a long time ago. We just did e to the x and sine x. And I didn't prove this, but this is the formula. And you can see there's other common ones. All right. So we're going to refer back to this table. When you're doing the homework has a little pop-up table that you use. So I'm going to kind of show you how to do that. And also, we're going to do an integral, and we're going to do an integral of a function that is not an elementary function. It's just only going to have a Taylor series representation. All right, so here's the last example today. We're going to use the table to find the Maclaurin series for this. Now, this is x squared and e to the minus x squared. So we did the Maclaurin series already for e to the x. So I'm just going to substitute. Again, I'm allowed to substitute in constants and powers. And I can multiply. And then I'm going to use the alternating series estimation theorem to find this integral to 3 decimal places. So that's something we've seen before, but I'm going to show you how it's applied to Taylor series. Okay, we're starting with the Taylor series for e to the x. So this we proved it, but I'm also just, reading it off the table. And then e to the minus x squared, all you do is just plug in whatever the exponent is in for x. So in this case, it's minus x squared. Simplify if you can. So the negative alternates, we pull that out, and then what's left over is an x to the 2n, so that's kind of a separate thing. Now I want to find the Taylor series representation for x squared e to the minus x squared. But I can just multiply. So I'm just going to take this power series and multiply by x squared. So x squared times x to the 2n, well, that's just x to the 2n plus 2. So we've taken a known power series and manipulated it, right? Here's a multiplication problem. Here's a different exponent that could be of the form cx to the m. All right, let's do an integral. So this definite integral of this function that we can't do the antiderivative of this, we're not able to do it. I can just plug in the power series, right, the Taylor series. So it's just the power rule. When you do the integral, take the power up 1. The alternating part doesn't move, doesn't change. The n factorial is a constant, it doesn't change. But increase the power by 1, and then divide by the new power. Now the lower limit when I evaluate is 0. So if I plug 0 in here, the whole thing goes away. So all I really need to do is worry about the top. So I'm just evaluating this whole expression at 0.4. Now I'm going to break it out term by term. So I'm starting at n equals 0, then n equals 1, n equals 2. The reason I'm doing this is I need to use the alternating series estimation theorem, which means I need to see the values of each term. So the first way to do that is just break the whole thing open like this. Simplify if possible. And then I went ahead and just did all this stuff on a calculator. And what we see from the alternating series estimation theorem is that once the an plus 1 term is farther to the right than whatever we're interested in, then that means that the partial sum up to that value, but not including that value, the partial sum up to that value is, in fact, equal to this integral, but to the number of decimal places specified, which in this case was 3. So this one is zeros to 3 decimal places. So you sum up these two, and the sum of the first two terms is correct to 3 decimal places. So that's how you do it. You can build these custom functions. We wouldn't be able to do this integral by hand, but change it to a power series, do the integral. We only need it to be correct to 3 decimal places. As soon as our third term is less than 3 decimal places, we're done. Add up everything else, and that's the alternating series estimation theorem. All right, well, that's everything. So let me know if you have any questions, and I'll see you next time. Bye-bye.